Hello, everyone. Today we will see section 2.5, identity of set. So I hope you are doing good today. Today we will introduce what is compatibility, what is countable set, and what is compatibility. So let's review the definition of set. What is a set? Why? Okay. Anyone can tell me the definition of a set? What is a set? Because in your major examination, we will have 2 days, Tuesday and Thursday. On Tuesday, you will have a lot of questions. You need to answer the definition of different terms. And then on Thursday, you need to answer different questions. So we will have 2 days for our midterm examination. You need to answer what's the definition of different terms, such as what is a set. All right. How about elements together? Not exactly, because when you talk about elements, we have, for example, sequence. We have a sequence, then we have the order of each element. So you consider a sequence that are one. If we have a sequence of elements in order 1, 3, 5, 7, and so on, you consider it is a set. Yes. Okay, so if you can see the definition of a set, actually it is an ordered collection of objects or elements. Okay, so we don't actually consider it ordered. So you may have 1357. You can also have 3105. They are the same. And next, what's the definition of commonality? It's the number of elements within the set. For example, I have 1, 3, 5, 7, 4 elements in this set. And the commonality of this set is 4. Okay? So after a quick review of the definition of set and commonality, then we can see how we define equal commonalities. If we have a set A, its commonality equals to the commonality of set B, then we know this is the notation of commonality. We can write commonality A equals commonality of the set B. Okay, so when we call equal commonalities, that means we can only if there's one-to-one correspondence from A to B. Okay, so you need to map each element from A to B by one-to-one correspondences. Then we can fully make sure that the commonality or the number of elements equal in set A and set B. Okay, and later on you will see how the question asks you to prove a one-to-one function from commonality A to B. Then you can write the commonality A less than or equal to the commonality of the set B. If you can find only one-to-one function, so we just define one-to-one correspondence to indicate their commonality are equal. But if it's just one-to-one, then you can consider maybe we have multiple elements from A to the element B. So the commonality could be less than or equal to B. Okay? And then when you want to prove that commonality A is smaller than commonality of B, then one thing you can do is you can prove A less than and equal to B. To assert there is a one-to-one function, then you can map the element from A to B. So this is equal to 2. And then you can prove that A and B have different commonalities. So that means if less than equal to is 2 and they are not the same, then we can assert that commonality of A is less than commonality of the set Okay, just some strategies to help you to prove, once you need to prove the cardinality, if they are equal or less than or equal to or less than. All right, next let's see a new definition of finite set. Okay, so if S is a finite set with cardinality n, and A is a natural number, then we can say the set S is finite because you can actually count 1, 2, 3, 4 to n. Okay, so if you have a fixed number of n, then we can call this set a finite set. Okay, so on the contrary, it is infinite set. It is not finite. Okay, very simple definitions for the set. All right, next let's see some properties of the cardinalities. If S prime is infinite, then the subset of S is also infinite, and if the subset of S, then S is infinite. Okay, it's very intuitive. If S prime is already infinite, then it's a subset of the set S. That means S has larger cardinalities than S prime, then S must be infinite. Okay, every subset of a finite set is finite. Because the large set is already finite, you can count 1, 2, 3, 4 to n. And then when you extract the subset of that set, the subset is also finite. If you have a function x to t is injection, and x is infinite, then t is also infinite. Because it's injection, right? So injection means the cardinality of s is less than or equal to t. And when s is infinite, then t is larger or equal to the cardinality of s. So s t must be infinite. All right. Next one, if s is infinite, then its power set p of s is infinite. So we know the cardinality of a power set ps is larger than the cardinality of s, right? If you have only two elements A, B in the set S, then the power set will be empty set. The element, the set contain A, the set contain B, and the set contain A. So you will have four elements within the power set P of S. Okay, so you can see when S is already infinite, the power set will be also infinite. Next one, if S and T are infinite set, then its union is infinite. Okay, so please write down on your paper what's the definition of union of the set S and T. Maybe you will see this question in your midterm examination. I believe you can answer this. S is 0, 1, T is infinity. And what's the union of S and T? I know you can answer that, but how about write the definition of the union of the set? If you don't remember, you can check the section 2.1. Okay, actually we can collect element of A when A is in S or A is in ST. Then we collect all that elements, and this will be S union T. Okay, so we collect all elements either in S or T, then we put all these elements into a new set. Okay, so let's go back to property 5. If it's an infinite set, then it's infinite. So very intuitive, right? Next one, if S is infinite and T is not empty set, then the Cartesian product ST is infinite. So maybe I'd like to invite someone to explain the definition of Cartesian product. Very similar to this. Okay, how about you? What's the definition of Cartesian product of the set S and T? We have a set, we collect the element of A, and what's the property of this element? Okay, so 把每个东西拼在一起。Okay, so when you talk about you combine these elements, okay, that means actually we are collecting order pairs A and B in this set. And we need to follow some property. A in the set S and B in the set of T. Then we collect all these order pairs. Then we have the set, the Cartesian product from S to T. Okay, so that means 你把它拼在一起。Okay. So you need to write in mathematical language, then you can answer the midterm examination. Alright? Alright, so let's go back to property 6. If S is infinite and T is not empty set, then the Cartesian product S. So maybe you can follow this definition from the element A is extracted from an infinite set S and B from a non-empty set T, then the Cartesian product will be infinite, right? Because when you extract all the pairs, the number is infinite. Alright, last one, if S is finite and T is not empty set, then the set of functions from T to S is infinite. Okay, so because we already have infinity set S, so when you define any mapping functions from S to T, or from T to S, okay, then you will have infinite set of functions. Alright, next, I would like to introduce a new definition, countable and uncountable set. So let's see this definition. A set is either finite or has the same connectivity as the set of positive integers plus, which is called countable. Okay, so by the literal meaning, you can countable means you can actually count 1, 2, 3, 4 of this set. So if this set is finite, then you can actually count 1, 2, 3, 4 to n. So that means this set is countable. Then we have the second case. If it has the same connectivity as the set of so we know positive integer 3 plus actually is 1, 2, 3, 4 to infinity, right? So we don't have the number of that set, the number of connectivity. But you can count that set 1, 2, 3, 4, 1 by 1. Okay, so although it's infinity, actually it's still countable because you can count z plus from 1, 2, 3, 4, 1 by 1. If you have the previous one, then you can count the next one until infinity. So we define this as countable set. A set is not countable if it's uncountable set. Right? For example, we have the set of real numbers, which is an uncountable set. Because we will see the proof why we cannot count real numbers. first one, second one, next one. All these real numbers. We will see the proof later. Then we will give a name of the cardinality of positive integer to plus, because we know it's an infinite number, 1, 2, 3, 4 to infinity. So we don't have something like finite set. Okay, for finite set, we have the cardinality n to indicate that is the cardinality of S. So if you have apple, banana, strawberry in the set, then the cardinality is 3. But if we have Z plus, that means we have infinite number of this set. Then what is that cardinality? Alright, no problem. We can define a very special character element now to indicate that's the cardinality of infinity set. Okay, for Z plus. Okay, so although it is infinity, it's alright because we can still count 1, 2, 3, 4 to next. So we call this countably infinity set. Now we have the cardinality for this set. We can count, and this cardinality is valid now. This special character, although it's infinity, right? So for such case, we define this cardinality as this special character valid now. All right. Based on these definitions, next we can see different questions to ask us to show if a set is countable or uncountable. Okay, so firstly, let's see how to show that a set is countable set. Alright, so let's see. If the set is countable, if it's possible to list the elements in the set in a sequence, especially if the sequence is indexed by a positive index. So if you remember the definition of section 2.4, the sequence, what we define sequence. Okay, the sequence means we have an older collection of objects. We have A1, A2, An in a sequence. That means we have some objects, but we have defined the order of each element. 1, 2, 3, 4 to N to infinity. Okay, so that's how we prove that it's countable. Because once we can map the index 1, 2, 3, 4 to N, map to the element 1, A2 to An, that means we can count those elements and we know the commonalities. So next we will see, this is a very strong condition. If and only if we can use the elements in a sequence, that means we try to assign a number 1, 2, 3, 4 to N and assign to each element in the index in the set. And we can call this is a countable set. Because we actually count its A1, A2 to N by the sequence. Alright, before we jump into the examples, let's see a very interesting problem which is called Hilbert Square Hotel. So consider you have a very special hotel. It has infinity number of rooms. Okay, so let's see, we have 1, 2, 3, we have infinity room of this hotel. Then let's see, we can always accommodate a new guest at this hotel, even if it's fully booked. Okay. So let's see, if each room is occupied by a guest, and this hotel is fully booked, all right, we can still welcome a new guest here. How? It's already fully booked. All right. The trick is how we can move the guest to the next room. Because the room is infinity, so you can move the guest to the next room. So room 8, the guest can move to room 9, and guest can move 7, move to room 8. And then we can have an empty room for the new guests. Okay, so I hope it won't sound very weird. Why a fully booked hotel can welcome new guests? So that's the property of infinity numbers, so which is called Hilbert-Graham-Field problem. Next, let's see how we show a set is countable. Okay, so we need to have our own way to assign the number 1, 2, 3, 4 to n to each element in the set. Once you can assign the orders of each element, then it is countable. Alright? So let's see our question. How we show that a set of positive even integers is a countable set. So we can list all positive even integers, 2, 4, 6, 8, and so on. Then we need to map to the order 1, 2, 3, 4, and so on. Okay, so next, let's see how we discover the mapping function, how we map the order 1, 2, 3, 4 to all these elements set 2, 4, 6, 8. Okay, if we can define the function fx by 2x, then if x is 1, 2, 3, 4, then fx equals 4, 2, 4, 6, 8. Okay, so now we have these mapping functions. We need to prove that this function is one-to-one correspondence. Okay, so first thing is we show that it is one-to-one. Okay, so remember the definition of a one-to-one function. If we have two elements mapped by different elements from set A, we need to show that these two elements are the same elements. Okay, so this will be easy by the function f of x equals 2x. If 2n equals 2m, then n equals n. That means if we have two different elements, then they should be mapped by the same elements in set A. Okay. Then we can prove that this one-to-one function. And then we need to prove it's also on 2. Okay, so you can choose either arbitrary elements from the set. So you can write the set t equals to k because we have even integers. By the definition of even integers, you can write the number to k. So that means we have some positive integer k that maps take t. Okay, so every element within the set, you can find what element is A and map to the element in set B. So it will be on 2 function. Okay, now we prove that when you map 1, 2, 3, 4 to all elements of the set, it is one-to-one correspondence function. So that makes this set countable because we actually count this is the first element, this is the second element, and you can count one by one. Alright, next let's see how we show the set of integer z is also countable. Because the integer z contains negative integers, positive integers, and 0. Okay, so we can arrange the numbers of integer z like this. 0, 1 minus 1, 2 times 2, 3 times 3, and so on. Okay. And then we need to know how we map 1, 2, 3, 4 to these integers. Then we can define the function. If it's even, then fn equals n divided by 2. Because you can 2 map to 1, 4 map to 3, 2, and 6 map to 3. Okay, so how we map the index to the elements is f of n equals n divided by 2. And then when it is odd, then you can see 1 map to 0, 3 map to minus 1, and 5 map to minus 2. Okay, so it's actually n minus 1 divided by 2, which is mapping odd. Alright, so when we define the mapping function, actually we can count all these positive, negative, and 0 integers by the order 1, 2, 3, 4, 5, 6. And then we prove that this set is a countable set. Alright? So Just give me 1 sentence how to prove a set is countable. Write down on your paper. Once you have different questions in the midterm examination, ask you to prove that a set is countable. How to prove a set is countable. 好，那个青红色外套的男生，如果你要我要先放的话，问题呢就是我们要如何证明一个 set 是 countable set？用一句话来回答。好，不确定的话，前面的你先。Mm-hmm. So you need to define your own functions to how to arrange their orders to make them map to order 1, 2, 3, 4, 5. Once you can find the mapping function, then you can see the first element is then that's how we count. First one, second one, second one, and 1 to 1. Okay, then we can make a countable set. Alright, next let's see the definition of rational numbers. We have seen this before. If we can write a real number into the form of p divided by q, and q is 0, then this number is a rational number. Next, we want to show that the positive rational numbers are countable. Okay, so it's not that easy. It's not 4. It's not -1, 1, 0. Okay, it's all positive rational numbers. So how we prove that it is countable? Right, remember that sentence. We need to arrange all elements in a sequence, and we can see which one is the first element, second element, third element. So if you can map 1, 2, 3, 4 to all these rational numbers, then we prove it a countable set. So this is how we prove arrange its order. Alright? So by definition of rational numbers, we can write a number into the form of p divided by q, and pq is integers. Alright? And then q is not 0. So actually you can write all numbers within the matrix. We have the numerator 1, a denominator 1, and we have the numerator 1, 2, 3, 4. And then we change to 2, and then we have 1, 2, 3, 4. So for each row, actually you can list all these elements by the order of natural numbers. And below this is numbers, right? So this will be a very large matrix. But we can define the order from the left top corners as the first elements. And then we scan all numbers in the exact same order by this order. And then we just define the first element, 1 divided by 1, and then 1 divided by 2, 2 divided by 1. Remember, we have some repeating elements. For example, 2 divided by 2 actually is already held as 1 divided by 1. How many these elements? So just pass these elements. So you can see actually we have circles of these elements. That means it will be considered our orders of these systems. Alright, so this is how we arrange its order. So you need to prove that, just like our previous example, once you define the order, then you need to prove that it's 1 to 1 and on 2. Right? So we can explain this part because actually if you define this order, it's actually 1 to 1 corresponding. So this is how we prove that the rational numbers are also countable sets. All right. Next, let's see a new definition: enumeration. So, enumeration is a certain function from n to x. Okay. So, if you have an arbitrary set x, then you can define how to map n to x. For example, you have 4 elements in ECD, then you need to have a certain function how to map the segment n to x. Right? So if S is also injective, then it's a enumeration without repetition. If it is not an injection, then we have repeating patterns in this enumeration. Let's see this example. If we have S has 4 elements, alpha, beta, gamma, delta, then we can map natural number segments, for example, 1, 2, 3, 4. This is a substantive function. So it will map all elements. If you map 1 to gamma, 2 by alpha, actually we have a enumeration which is called gamma, alpha, and beta, and delta. Okay? So when we have repeating patterns, you can also map 1 to 6 to this set. Okay, then we have the enumeration. 1 is alpha, so we have alpha here. Then 2 is gamma, we have gamma. Then we have beta, delta, and alpha. Alright, so you can see actually compared to the original set S, this is the enumeration with patterns. Okay, so I don't know if you have noticed the important part because the definition of enumerations actually is map n to S. So if you can find such enumeration, that means you assign 1, 2, 3, 4 to the set S. So this gives us a very useful tools. If S is countable, then we can use enumeration of S. Because we know how to enumerate, that means we know how to assign 1, 2, 3, 4 to the set elements of the set S. That means S is countable. Okay. So remember, we have such tool. Once you prove this set is countable, you can use the enumeration. If the enumeration exists, then it's a countable set. Okay, next let's see strings. Let's see this example. If we have a set of finite string S over finite alphabet set sigma, then the set is countably infinite. Okay, so let's consider what is finite alphabet set. Just like our English alphabet, A, B, C, D to Z. So totally we have 26 alphabet. Okay. And then we can use this alphabet set sigma to form the English words. Okay, that will be finite string. For example, we have I love you. Okay, I love you basically they are finite strings because I is the string with 1 character, love is the string with 3 characters, and they are formed by the finite alphabet set into Z. Okay, so if you understand the example, what is the question? Then you need to show that the set of finite string is countably infinite. Okay, so now we know when we need to prove that it's a countably infinite set, we need to assign the natural number 1, 2, 3, 4 to n to infinity. decide the order of this set. Okay, the method is very easy because we can choose all strings of 0 lengths of the string. And then you can choose all the strings with length 1 by its lexical graphics of the and then we choose the string of length 2, length 3, and then we can make a ordered list. Let's say this example. If we have the finite alphabet set A, B, we don't have one A to Z, we only have 2 alphabets. And what kind of finite strings we can form? If the length is 0, then the string is empty string like that. But when we have length equals 1, okay, and then we have only 2 strings, A and B. So we use A first and B later. This is what is called by its lexical order. Okay, then we have the string with length 2, then we use A, 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 B, B, A, B, B. Okay, now we can assign the order. Once we can construct these finite strings, and this is 1, 2, 3, 4, 6, 7, 8. Okay, so by these orders, we can list all these finite strings by its order 1, 2, 3, 4, 2, 3. Okay, so this is how we prove that the finite string set over a finite alphabet set is completely next, let's see a very weird example. Show that the set of all Java programs is countable. Okay, because we know there are so many Java programs, but if you collect them in a set, how to show that it is countable? All right, remember when we need to prove it is countable, then we need to assign the order 1, 2, 3, 4 to all Java programs. Let's see how we prove that it is countable. Okay, so the first step, fit any strings into a Java compiler to see if it is a correct Java program. So you may have different combinations of strings. The string number may be 3, we can set all Java programs, all strings into the Java compiler to see if it is the correct Java program. If the compiler says yes, then we put into the list 1, and then we jump to next candidate string. Then we can examine all combinations of finite strings to examine if it is Java program and put them in order. That's the way we show that all Java program is countable. Okay, so you can see by this proof, we don't actually have a fixed function f of x equals something, but we find how we enumerate all elements within the set. If you can actually put in order a discovery order 1, 2, 3, 4, and prove that it is 1, correspondence, then that's how we prove the set is countable. 好，到目前为止有没有什么问题？可以吗？好。All right, if no problem, then next we will see how we prove a set is uncountable. Okay, so we mentioned that the real number is an uncountable set. Next, we will see how we apply a very special strategy, which is called interdiagonalization argument, to help us to prove that real numbers are uncountable sets. It is not easy to prove a set is uncountable. So usually we assume it is countable set, and then we derive the contradiction. So by this, we assume the set of real number is countable. Okay, and then we have the properties mentioned before. If real number is countable, then smaller subset is also countable. So we select subset from 0 to 1, just a small range of real numbers. But if R is countable, then its subset is also countable. So 0 and 1, all real numbers with this range is also countable. Alright? Then, if it is countable, then by the definition, we can list all real numbers 0 and 1 in order. R1, R2, R3, R4. Right? And then we have the representation for each real numbers. We have 0.7. Okay, so this is the first digit of the decimal part. We call that P11, because it's the first digit of the first element of 1. So we have P12, P13. That means the second digit is the third digit of this decimal digit. Right? So far, we just follow the assumption if R is countable, then the real numbers between 0 to 1 is countable. So we can give a list R1 up to R3. Next, the most important part is the trick in step 4. Now we have a new real numbers and want to prove that it's a contradiction. Okay, so we have rules to have a new real number. Okay, the rule is if I equals 3, then we make SI equals 4. If it's not 3, then we make SI equals 3. So let's see this new real number. For its decimal part, we have the first digit x1, second digit x2, third digit x3. So we need to determine what are the numbers of each digit. So our rule is we compare to DII. So let's see. This is D11. So you can check if D11 is 3 or not. If it is 3, then we assign XI, that means it's 1, 4. So if this one is 3, then this one is 4. If this one is 3, this one is 4. If this one is not 3, then this one is 3. Okay, so you can see by this case, we have a new real numbers R, which is not in the list, because R does not equal to any numbers of this list, because x1 is not equal to 1, 1, x2 is not equal to 2. So if you can have this list, then I can give you a new real numbers R that is not in this list. So this tells us actually not all real numbers can be put in order in a list. So this is contradiction. So why we have such contradictions? Because we assume R is countable. So this leads to the contradiction. We cannot have the list of the real numbers within 0 to 1. Okay. So if we have a countable set between 0 to 1, that means the larger set R is also uncountable, because its subset is uncountable. So the large original set R is also uncountable. Right?我们就是假设它按照字典的方式把它排下来，所以我们真的排了，我们排了R1、R2、R3。我们排了，但是现在呢，我们 always 可以找到一个新的数字，这个数字是你无法排在你的清单里面的，所以就告诉你，其实你排不出来这个数据。还是你可以想想看，如果你想要知道字典的排法的话，你可以怎么排？然后，如果按照字典的排法，其实就可以把它排出来。 按照这点方法，我们只要用品特三角形的方式，即使按照这点方法排，还是按照它是不在这个。
刚上面的那个，我们也可以照这个，就是你可以照那个写的这种，就是我是给那个，如果不是，
但是它就不会通过Java compiler 了。
那在上面那个，
这个，
就是对吧？就比如还有 A
对，
它一样也照那个。
OK， 好，这个差别就在于说，因为这个是一个 finite string， 但是我们刚刚的那个 decimal 的 representation r 它是无穷的数。所以如果它是一个 finite 的话，你是没有办法按照刚刚的方式找出不存在的。只有它是 infinity 状态才有办法这样做。
而这个的长度是可以一直拉长。
没错，但是对，但是长度可以拉长的意思是说，对每一个都是有限的，但是刚刚的那一个数字是一个无穷的数字了，这样。你再想想看好了，好，或者你可以把你想的那个证明的方式写下来，然后看看哪里会出错。如果你把那个方法证明写下来，然后我们再来一起来看看是哪里出问题，你就把这个写下来，这样，然后用刚刚可能在讲的这个方式来证明，好不好？Okay, next let's see a theorem. Every infinite set contains a countably infinite subset. Alright, so this is very intuitive, right? Infinite set contains a countably infinite subset. Okay, so now we can have this, how we derive this countably infinite set. If we call that countably infinite, that means it's countable. So we need to know what's the order of the elements of the subset. Okay, so let's say it's true. If S is an infinite set, then we can select a sequence of elements by this order. For example, for the original set S, we choose A0. This is the first element. And then we choose the second element A1, but we choose from S exclude element A0. And we choose A1 from the rest of the elements of the set S. And then we can repeat this step. So that we will have A1, A2, A3 to infinity. Okay, then that will be a countable infinite subset of the original set S. Okay, so the theorem asks us to prove that every infinite set contains one countable infinite subset. This is how we construct this countable infinite subset for all infinite sets. Okay, so let's see. This is also a mapping from N to S, right? We have A1, A2, A3 to infinite number. Actually, we are mapping natural number N to the subset A1, A2, A3, and so on. Okay, so that will be a countable infinite subset. All right, next let's see another theorem, the union of a countable collection. Countable subset of a countable set is countable. Right? The union of a countable collection of a countable set is countable. Okay, so that means if you have one countable set, then all its subsets are all countable, right? So if we have the set S, then you may have the subset S1, S2, S3, different subsets, but all of these subsets are all countable sets. So if you calculate the union of these countable subsets, it's still countable. right? So let's see. We apply the same tricks. When we need to prove it's countable, then we need to apply into S, okay, into our target set. How to enumerate all elements in the order 1, 2, 3, 4. Okay, so let's see. If we have countable collection, countable subset S0 is 1, S2 from the original countable set S. Then we can have the union of this countable collection by this step. If we have S0, S1, S2, S3, and so on. Okay, that's a countable collection, countable subset from the original set. Then we can have its element A0, and for the subset S1, then we have all its elements A10, A11, A12. So you can form another matrix to represent all elements of this subset S0 to S3 and so on. Okay, even this is okay. So it's very like the example how to prove the rational numbers. So we can apply the z-net scale orders to put the order of all elements of this. And once you can put the order into the element A00 to others, then we just define the order, how we count. Then the union of this subset is a countable set. All right? Next, let's see another theorem. If sigma is a finite alphabet set, and sigma star is the set of all strings over sigma, then prove that the power set of sigma star is uncountable. All right, so maybe we can see our previous question. All right, if you remember these examples, we have finite string S over finite alphabet set sigma, which is countably infinite. So you can see the finite string set S is already countably infinite. How about its power set? Okay, now the theorem tells us if you have a set of all strings, the string is constructed based on a finite alphabet set, sigma. Okay, then sigma star is just from our previous example before. Then the power set of that set is uncountable. Okay, so there's one thing you can notice. If we have a countably infinite set, sigma star, then its power set will be uncountable. This one is countably infinite, so its power set is uncountable. Okay, let's see how we prove that the power set of sigma star is uncountable. So let me give you a real example here. If we have the finite alphabet set sigma, that will be the English character A, B, C, D to Z. All right, and then we can use this alphabet set to construct our strings, sigma star. So we have the string I love you. Okay, so we have so many. We already know this is countable infinity, right? And then what's its power set? Okay, remember the power set we start from empty set. And then we have I love you because it's subset. And then we can choose I love you or I love you into the subset. Okay, so now we know what is sigma star is the power set of sigma star. Now we want to prove that the power set of sigma star is uncountable. So remember our tree, we assume it's countable, and then we provide the computation. And we can prove that the power set of sigma star is uncountable set. Okay, next, we'll see if it is countable, then we can find find the enumeration of the power set of sigma star. If we cannot find the enumerations, then it is so we already know this is only conditions. Let's how we derive the contribution. Okay, so let's see this notation. If we have x0, x1, x2 be an enumeration of strings of sigma star, and we have a0, a1, a2 is the enumeration of the power set. Okay. And then we can construct the matrix, which is a binary matrix as follows. Okay. So this is the first subset of the enumeration. Okay. Then we have a0, a1, a2. And then we can see the element x0, x1, x2 is in this subset over R. Then we give binary numbers 1 or 0 to the number. Okay, so let's see. So let's just use our example. I love you. All right. So if this is I, this is love, this is you. Okay. And then this is the subset. For example, this is subset contains only I, and this is a subset I love, and this is the subset I love you. Okay, and then we have the binary representation for this matrix. Okay, if I is in the set A0, so this number is 1. And love, this word is not in this set I, so we have 0 here. And you is 0. For the second set, it has I love, so we have I1, love 1, and you 0. And for the next set, I love you, it exists in this set. So we have 1, 1, 1 for this representation. All right, is that clear enough? We just use our example. We have the power set, for example, empty set. I love you, I love you, or I love you. Okay. It's all different subsets. And then we consider if this string I love you within the set or not. So we can construct this binary representation. This is the set contains only I. This is the set contains I love. This is the set contains 3 strings I love you. Okay. So this is our columns. For our rows, we have all strings here. So if our first string is I, second string is love, and third string is you, then we can see if this string is this set or not. So if this is a set contains only one string I, and I in this string, so we will have 1 here, because I is in this string. So we have the binary representation 1. But for other strings, love you is not in this set. This set contains only the string I. So we have 0, 0 here. Okay, so let's move to A1. If A1 contains the string I love, then we have 1, 1 here. We don't have you in this set. So by the element A1, 2, this to be 0. Alright, so let's see the dimension. If xj is the set AI, then we assign aij to 1. So I hope you can map to the index by yourself. If x is not in this set, then we set this position to 0. That's how we form the binary matrix. Okay, so now we will apply very similar tricks to Cantor diagonalization. Then we assume all subsets within the power set can be listed here. So we just list A0, A1, A2, because we assume that power set is countable. So how to make power set countable? You need to list all its subsets by the order 1, 2, 3, 4. So we're just trying to put order of all these subsets. Empty set. I love you. I love you. To 1, 2, 3, 4, 5, 6, 7. So that's how we do it. We have the order A0, A1, A2, A3, A4, and we put them in order because we assume it's countable. Next, we want to derive the contradiction. Okay, let's see how we derive the contradiction. Very similar to Cantor diagonalization. If aii equals 0, then we put the element xi into a new set A. Alright? So that means we only consider the diagonal elements of A0, A11, A22. Okay? So if aii is 0, that means the string is not in this subset. If it is not in this subset, then we include this element into this set. Okay. If it is 1, then we exclude this element. We don't want this element because this element is still in this element in the set A1. Okay. So by this fashion, actually you can construct a new subset A. This set A is not equal to A0, A1, A2, Okay, this tells us, actually we assume we can have a list here, but we can always find a new set that is not within the listed subset A0, A1, A2. Okay, so this is a contradiction. Actually, we cannot list all subsets within the power set because you can find the new set A. This set is not equal to A0, A1, A2. This is how we derive the contradiction. So this tells us our assumption, the power set of sigma star is not countable. Okay, so we may have more formal ways to prove. So if we let A equals Aj, because our new set A is not equal to any subset A1 into A3, but we assume A equals some Aj, and we try to derive the contradiction because we cannot just prove by compare A to Y, A2. Okay. So we assume it's equal to some Aj subset, and then we try to derive the contradiction. Okay, so let's see. If we assume A equals Aj, that means we have some strings Xj that Ajj equals 0. If Ajj equals 0, that means the element, the string Xj is not in Aj. Okay, so A cannot equal to Aj. This is the contradiction. So the contradiction is led by the definition because once A equals to Aj, then that means by the definition of the set A, Aii is 0, and Xi will include it. So in this case, if we assume J, then J is 0, So this is the contradiction because Xj is actually in the subset Aj. Alright? 好，那我们请这同学帮我们用中文解释一下好了。好，看看这个证明是怎么完成的。好，那个书卷讲的，帅哥要不要帮我们记？
假设一个 set A，然后它包含了所有的字串，然后这些字串在一个那个然后我们发现这个 A 没办法是我们刚刚排好的那 A0、A1、A2，它不能是里面其中的它又是一个这个 A 又是一个 power set，但是 A 不在里面，所以这个 A1、A2 应该都是不存在的。
OK， 好，那我们怎么证明这个 A 完全不在这个 list 里面？
那就是用那个下一页，假设它有，然后就是会再发现，假设是错，所以它这个假设是错，那就代表说 A 不等于 AJ， 那就代表这个 A 不在我们刚刚已经排出来的那个序列里面。
OK， 好，好，那我们可以看一下这个定义哦。实际上呢，假设 A 等于 J 的话，好，那我们就来查一下 AJ 这个 element。那从这个定义来说，如果这个 AJJ 等于0的话，那 I 这个字就会被拉到 A 里面去。好，那实际上 A 呢是这个集合是我去收集所有的 SI 不在 A 里面。好，所以如果它收集它等于 AJ 的话，好，那就相当于它的 XJ 这个项目并不会在 AJ 的项目里面。你会发现它不在里面的话 ，XJ 就会被放到 A 里面去，所以实际上它根本就不可能等于 AJ。好，那我们就用这个方式来说明，实际上你可以把 J 推广到任意一个在 power set 里面。那如果 A 等于任何其中一个 power set 里面的话，都会有这样的存在。因此，就是说它的 power set 是没有办法像我们想象的用一个电平台的排列的方式把所有的列出来，这样子的事情是列不出来的。好，就跟我们前面在介绍 real number 的时候，我们说我们可以把 real number 用 R1、R2、R3 排出来，好，实际上我们也会得到矛盾。好，只要用 Taylor diagonalization 就可以证明你所谓的能够排得出来的事情是错的。All right, we have a few slides left. Let's see some questions about uncountable set. Can we compare the cardinality of uncountable set? And if we have a set of real numbers between 0 and 1, and the power set of single star, we already know is uncountable set. Now we have two uncountable sets, the real number and the real number between 0 and 1. And we also have the finite string over finite alphabet set, single star, its power set is uncountable set. So if they are all uncountable sets, can we look at them as the same cardinality? Because we don't know, we cannot count, so we just assume they have the same cardinality. If it is true, and the next question, Their uncountable set S1 and S2 is cardinality S1 is listed and S2. So the question is very obvious. Can we compare the cardinality of uncountable sets? Next, let's see this question. So now we have a formal definition for the cardinality of uncountable set. If a set S is of cardinality C, if we can find a bijection function from 0, 1 to S, then we use the cardinality C. In any case, it's the cardinality of this uncountable set. Okay, so we call this a continuum. If you can map the 0, 1 to the set S, then we call the cardinality of that set is C. Actually, we know it's uncountable, right? But now we give the cardinality of that uncountable set. We use the label C to indicate its continuum between 0 and 1. Right? So this is a new definition, just like the alif now. We cannot count countable infinite set, but we give a special character alif now as its cardinality, just like we did right here. So we give label C to indicate the cardinality of from the range 0 to 1. This is the countable set. Now we define its cardinality is C. All right. So next, let's see the next theorem. All right. If S is a finite set, then the cardinality of S is less than alif now is less than C. Okay. So remember when we need to prove the cardinality is equal or less than and equal. Okay. We need to determine if we can find a 1-1 mapping function, or if we can find this 1-1 function, then we can claim at least it's less than and equal to T. Okay. And then we need to prove they have different cardinalities. Then we can claim X is equal to T. All right, maybe we leave next time. OK， 好，那今天的内容看同学们有没有什么问题？好，大家都苦笑连连的哈。那麻烦大家回去再好好听一下我们上课的影片哈，然后把这个章节能够弄清楚。好，那我们今天就上到这边。
然后想要问一下那个，中考试的要考2次。
对，2次，星期二考第一，星期四考就是各式各样的题目。
好，谢谢。
I have a question that I don't know if it's with your assistant,
Mm-hmm.
but last week I wasn't there because I was sick, so I wanted to know what I should do. Like to justify my absence?
When you hand this paper, then we will record.
Yeah, I know, but like just last week I wasn't there because I was sick.
All right. So you can give me your applications to claim your sick.
Okay.
Mm-hmm.
Okay, so I have to go and claim because I did not wait to the doctor because I don't know doctor's here, but I can just...
I see. Once I have the formal applications to prove that you are sick, then it's okay. You will not record it as absent of the class that day.
But how can I have the formal application?
You need to ask the department office.
Okay.
Mm-hmm.
Okay.
对，因为我们上完2.4之后就会有一次作业了。我们是4月14号在交的。
对。
我们 equals 上面的投影应该有这个吧？
可是我上面是不知道，然后这个是
真的吗？哦，
这个不一样。
好，那我再更新一下好了。
我想问那个期中考的时间。
就是学校定的期中考中这样子。也是7月20。
那不是16周？
是20吗？我记得好像是17号那周。是不是？哦，你讲对了，20号那一周没错，对，20号那一周，所以我们就是21、23这样。对，期中考这样。我再请助教公布一下啊。
是17周还是16周
？16周。
所以我是16。
好，来，好啊，你讲一下。
我是说，我那个是做实训的时候不是。
对，没错。
好，那我们把它范围缩减到 A 到 J， 然后 A 就对应到0，然后 J 就对应到9。
你讲的这个 A 对到 J， 0对到9是你等一下，你现在讲什么问题啊？你现在想讨论什么问题？
我想要讨论这 real number 为什么是 uncountable。
OK， 好。
我想要从训去考。
对。
real number 是考。
OK， 可以，好。
我现在做 A 到 J， 那一样
对。
刚刚前面讲
对。
然后我把 A 换成 0，然后 J 换成 B 换成 1，C 换成2。
对。
然后 J 换成9。
没错。
然后这样，然后全再加上0，那就是
对，没错。然后呢？
这样不就说明了，就是 real number 是 countable。
没有说明啊。那你按照你现在只是试着把它排出来，所以你刚刚已经得到我们证明无理数那一题的 R1、R2、R3、R4， 你已经把 R1、R2、R3、R4全部排出来了，对不对？因为你已经把它排成这是0、1，这是0、2，这是1、2，然后你还有3，前面再加0点嘛。所以你其实像这个排法，你的 S1、S2、S3 就是把刚刚所有的 R1、R2、R3 全部都排出来，对不对？
对。
你确定对才讲对哦，是吗？你现在做这件事情，它就是假设是排得出来的，因为只要它是可数的，它就排得出来。对。
那现在就是假设
排出来了。那然后你接下来证明啊？那本来在刚刚那边的证明的下一步是什么？real number。对，没错。对，没错。所以它的步骤是我现在建了一个新的数字出来。那你觉得你能不能建一个新的数字出来？它不在这个里面。照你讲的，它应该要能够，下一步应该就不能做了才对嘛。因为只要你能够把它全部列出来，你就没办法找出一个新的 string， 那个 string 是不存在在这里面的。那你按照刚刚的方式，你做看，能够找出那个不存在的 string 吗？
我觉得找不到啊。我觉得都列出来了。
那你试试看，为什么找不到？
为什么找不到？
对。
因为我们包含了所有长度音的示范，它的缩图，它所有长度的长度在组合。
对。
所以我没办法找出不在里面的长度一体，不在里面的长度，不在里面的长度一体，还不在里面的长度。它就这样1、2、3，然后一直到一个很大的数字。OK， 好，那我觉得它的差别是，我应该这样讲，就是说，你现在应该去试着真的找找看那个数，那个我们讲的那个新的按照刚刚的规则，在这个里面会是什么这样？对，你要真的去列看。照你讲的话，应该是列不出来嘛。
因为它跟第一个不一样，然后它跟这个的第二个不一样，它跟这边的第三个不一样。但是不一样的话，你会把它写成什么？那你自己定规则嘛。假设你现在有就是 A 到 Z， 或者你把这边全部变成1、2、3，你也可以把它变嘛。如果它是 A， 你就不是 A 嘛；它是 B， 你就不是 B 嘛。对，但是那一个东西是什么？你能够把那个东西列出来吗？
不是 A， 不是 A 写 B 啊，不是，如果是
好，那你把那个是完整的列出来给我看，因为这个题目是一个 finite string， 能够列出这个 finite string 吗？
finite string，
嗯。因为你看哦，你现在假设只要能够列出这个所有的 finite string 的 list， 那其实你要找的那个 string 它本身也是 finite 的，它一定会列在这个 list 里面。你其实是列不出来那个 string 的，所以你没办法用那样的方式，来证明它是 uncountable 啊。但你现在对，但是你现在想要用刚刚的可能对角形的方式来证明这个题目是 uncountable， 不是吗？你的问题，
然后说也可以。
我以为你要从那边是 uncountable 证明这个是 uncountable。但是你想要从这个是，好 ，OK。好，来证明它是 countable 这样 ，OK， 好，没问题，好，那所以你现在是用这样的方式来证明那边是 countable， 所以表示那边是列得出来的，但是我们刚证明的方式是你可以找到一个不存在的东西，
就是不在里面的数字。
对。
但是用这个方法写的话，好像像刚刚那样用
不存在的数字，对，你知道差别在哪里吗？为什么这样就不行了？因为我们这个题目它是 finite string， 只要这个 string 是 finite 的，你就永远没有办法找出不列在这个 list 里面的。但是因为无理数它是无限长的，所以你用 always 可以按照这样的方式去找到有一个不一样的东西，它是可以推到无限远的这样。没有懂我的意思是不是？
字串也是无限长。
没有，我们这个题目是 finite string 哦。我们这是有限的字母在有限形成的有限的 string。
对啊，我今天infinite string
对，没错，好，很棒，能够想到这个。同学说好像我的那个一个上的就是对，然后也公布一下我们那个期中考跟期末考的事情。然后我们那边是要考虑我们星期二会考定，星期四会考，就是然后我们的期末考就是学校定的16周的期末考试，所以那周的星期四跟星期四是我们期末考试，所以你在公布。